All right. Good morning, everyone. First of all, thank you, Magdalena, and the other organizers for inviting me here. It's a great pleasure. Yesterday, Thomas told us about his first encounter with Bjørn, and then I started thinking about what my first encounter with Bjørn was. And I couldn't quite pin down the exact conference I met him, but I do remember when I met his work first. And it was in my second year of thesis. My supervisor asked me to read into THH. And bear in mind, this was pre-Nikolaus Scholze, so the literature was quite hard to parse. And I was quite lost in this pile of articles until at some point I found this paper of Bjørn and McCarthy that was mentioned in Thomas' talk as well, about stable K theory being THH. And I started reading that, and I think it's the first paper I truly read, as in detail. And I found a lot of comfort into it, actually. And so I want to thank you for writing the beautiful paper, which was absolutely inspiring for me. Thank you, Bjørn. OK. Now let's get to some Witt vectors. So the characteristic polynomials bit is really an excuse for motivating this Witt vector part of the story that I would like to talk about. So let me start with that. So throughout the talk, I'm going to fix a ring. And at least for the first section, I'm going to take it to be commutative. Everything makes sense for non-commutative rings, but maybe not always exactly as I stated. If you are in doubt if the ring is commutative or not, ask, and I'm going to tell you. Ring and with involution, which you might take to be the identity. Sorry? Yeah, unital, associative as well. And we take, sorry?
Is it discrete?
It's discrete for now, yes. R is going to be discrete, and A is going to be a ring spectrum, hopefully. That's the idea. Let's see if I can stick to it. And then we take P, finitely generated projective R module, and F from P to P and endomorphism. Okay, so this is my table of notation that I'm going to try to stick to. Okay, and now let me remind you what a form is. So a symmetric form, non-degenerate, symmetric form on P is an isomorphism from P to P dual, which I define to be Hom over R from P to R, and which is symmetric. What does symmetric mean? It means that it's self-dual in the sense that if you do phi, I need to do this right, and you identify P with the double dual, then the dual of P is going to go in this way, and this commutes. Okay? And now, if you spell out what that means by adjoining this variable P, this means, let me write it, that its adjoint evaluated at a thing like that is equal to, well, you can flip the variables, but you do pick up a duality. Okay, and the bar is hidden in the way you define, I think, the module structure on P1, or the isomorphism. I'm not exactly sure at the moment.
Commutative is not important.
No, it isn't. Yeah, I mean, yes. So, okay, let's do this. So if P is an R module, this is a left module, but you have this involution, and so you can turn the left into a right module. Yeah. No, this is not where my life is going to become easier. It's going to become easier in a second. Okay, so anyway, this is a form you might have on a module. And then, so we say that, what about F? We say that F is phi self-adjoint if, well, it corresponds to its dual under phi. So what does that mean? If I do the composition the right way around, it means that F is the same as, you can do phi first, then you can do F dual, and then you can do phi inverse. Okay. And And, well, I guess I can call this the adjoint with respect to phi. Okay, so if P is free and phi is given by the standard forms, meaning given by the identity matrix under a standard basis, then this just means that F is equal to its transpose conjugate. Okay, so here's the key observation. That is quite simple. So if F is self-adjoint, then, and here is where it starts being helpful that R is commutative. You can look at the trace of F as an element in R. Otherwise, I would have to start modding out by commutators. But this is a well-defined element in R. And, well, if it's phi self-adjoint, this is the same as phi inverse phi dual phi. And now the trace has this amazing property that it's invariant under cyclic permutation of the entries. So this is actually the same as the trace of F dual. Okay. And now if you think in terms of free modules, well, I said that this is, the transpose conjugate. So the trace of that is the trace of F as an element of R with the involution applied to it. So this shows that the trace of F is an invariant under the involution on the ring. Okay. And now a very similar argument. In fact, so the same is true for the characteristic polynomial. And here is where having a commutative makes my life easier. So if you take the characteristic polynomial of F, it's going to be equal to conjugate as an element, for now, let's say in the power series ring. Okay, where the involution is on each coefficient. And if you think about it, you can write this in terms of trace of exterior powers, and because the trace is invariant, that's going to be invariant as well. Okay, and now I want to focus on that statement there, or this one. So this is a bad statement. Why is that? Because being a fixed point is a property, but being self-adjoint depends on phi. But being a fixed point does not. So can we say this? Can we improve this? In a way, and I'm gonna say in a minute what I mean precisely. In a way that depends on phi. For example, the identity is self-adjoint with respect to any form, and this tells you that, well, that one, for example, that the rank is invariant, and that doesn't depend on the fact you had a form to start with. So let me go here. So more precisely, here's what we want to do. We have the endomorphism of P and the characteristic polynomial, which sends us to, again, let me say for now, the power series ring. And up here we have the phi self-adjoint ones. Of course, there is a forgetful map down there. And so what we want to do, we want to fill in this diagram. So this map, right, so if we start from here, we know we land in the fixed points by what I said there. So what we would like, maybe, is to factor this map through something here. Some lift of chi to something here which maps down to the fixed points. Well, in a way that is not the identity, otherwise it will be fine. And if you are used to Mackey functor, this is exactly, what the kind of type of structure that a Mackey functor does, it gives you something that lives over the fixed points of something with an involution here. Yeah.
Maybe I misremembered something. So why is in this form of power series?
Well, I could say polynomials.
Yes, but you say that you want generality for non-commutative rings, or
Yes. Yeah. Right. R is commutative for now.
okay.
Otherwise, I would have to say something different that is more complicated.
Maybe mod out some commutator.
I'll tell you in a second. Yeah. One needs to take non-commutative with vectors, but because I haven't talked about it yet, I'm going to make my life easier and say commutative. I'm going to tell you in a second how to fix it for non-commutative rings. Okay, so that's the plan, or my motivation. I want to find something here that is a host for some lift of the characteristic polynomial for self-adjoint endomorphisms. Good. Now let's see. Okay, now let's talk about Witt vectors in the standard sense, because it turns out that that's a very convenient way of setting up the characteristic polynomial of an endomorphism in the usual sense. And then let me try to generalize this Witt vector to something a bit different. So let me review the characteristic polynomial. Okay, now here is where I'm start being a bit more precise of what I mean instead of the power series ring. So, and now R doesn't need to be commutative anymore. So here's the definition, and this is due to Achim and Thomas, is that you can take, if you want to define the Witt vectors of R, how do we do it? Well, we take power series with constant term 1, and we regard it as a monoid under multiplication. So if R is commutative, we are done. This is the Witt vectors. I guess this goes back to Atiyah and Toll, this definition. But if R is not commutative, we can abelianize it. And then we want to also quotient by a relation that tells you that 1 minus RST is the same as 1 minus ST SRT. Sorry. Okay, so you can flip the multiplications in the first coefficient. Now you need to be a bit careful. This abelianization and this quotient need to be taken in Hausdorff topological groups. So you need to quotient by the closure of the relations, but this is how to define it. It's a quite simple definition. And this is going to be my home for the characteristic polynomial. Now that I'm at it, let's define a variation. So given a natural number n, let me define the n-truncated Witt vectors to be those where you mod out the subgroup generated by the stuff of the form 1 minus r times t to the I, where r is in R, and I is coprime to n. Yeah, I mean, he defined it only at the prime p. So if you truncate at p to the n, then yes, then it is. Yes. Not completely obviously, though. Sorry? The first one, it's a relation. Well, it's 1 minus RST. So RS is a product of elements in R, and put in as the coefficient in degree 1. And the other one is the same where R and S are flipped. Yeah. Okay. So here's a theorem with Achim, Nicholas, Thomas, Irakli. So, I mean, I guess one can, I'm going to state a sort of streamlined version of it. So there is a map determinant from the Witt vectors of the endomorphism ring. And here, that's why you really need the version for non-commutative ring, because this is non-commutative, to the Witt vectors of R, such that, well, the characteristic polynomial of f is the determinant of, well, something in here, which is given by the class of 1 minus f times t. Okay? So 1 minus ft, I can regard it as a power series with coefficients in the endomorphism ring. And, well, the Witt vectors are a quotient of that by definition, and I can take its equivalence class. Okay. So this is one property. And I guess the other property is that, well, how is this determined? If you take its logarithmic derivative, which is injective on torsion-free things, so it's going to determine this map. And this is equal to, I hope I get the powers right, from 1, of the trace of f to the n. Okay. So if you take the logarithmic derivative of this map, it gives you some other power series, and the coefficients are given by the trace of the powers. Okay. Let's see. Other questions so far?
Shadow of this in some kind of K-theory?
Sorry, I got thrown off by the word shadow. Because yes, but in K-theory, you mean? Yeah, I mean, yes.
Oh.
So, I mean, the characteristic polynomial defines a map from cyclic K-theory into here, and that's injective. And the image is, so for R commutative, and the image is given by those power series which are fractions of polynomials.
Oh.
Yeah, so it's the theorem of Almquist and Grayson, I guess. Yeah. So yes, so you can see all of cyclic K-theory. Other questions? Okay. Let me give you a quick sketch of the proof of the construction of this map, at least, because I think this is quite nice. It's the following. Well, the trick is to extend this functor to the category of bimodules. Or let's say maybe, let me say of rings and bimodules. So that you can stick in coefficients in a bimodule. And then once you do that, you can do the following construction. Well, by extend, I mean that if you want to know what the value at a ring is, you can put in the ring with its canonical, regarded as a bimodule in the canonical way. Okay, I'm writing in F, sorry. In P. Okay, so that's part of what it means to extend the theory. I can put a bimodule in such a way that if I put the ring as a bimodule, then I recover the whole thing. And now here's the magic. So this as a bimodule this is P tensor P dual. And then there is this fantastic Morita invariance property or shadow or trace property of the Witt vectors. This is extra structure that you need to construct. that this is the same as the Witt vectors of R with coefficients in the two modules tensor the other way around. So P2 tensor over the endomorphism ring with P. And then once you're here, you have the evaluation map out of this, which is a map of bimodule. So you can apply that map, which is a functor, and so you land into the Witt vectors of R. And then this is the same as the Witt vectors of R. Okay, so that's one way of constructing that map. And okay, I'm going to stop here. I'm not going to insist too much on this. It's just to show how this characteristic polynomial can be built only out of the structure of the Witt vectors. And that's really what I care about. Yeah? Yeah, what did I write only? What did I write? Ah, I wrote F. Yes. No, of the determinant. That's right. No, you're right. Sorry. Yeah. No, absolutely. Let me fix this. What did I want to say? I want to say that. So, no, sorry. Yeah. I want to say the determinant of something. Let me not call it F. Of anything. Maybe I can say this. Okay, this is true. So if I start with something in Witt vectors in the endomorphism ring, applies determinant, I'll end in the Witt vectors. I can take the logarithmic derivative of that. It gives me a power series. This power series has coefficients. No, you're right. Okay. Yeah, you're right. So, okay. Yeah. Okay, let's say like this. Yeah, thanks. Sorry. Yeah. So you can describe the logarithmic derivative of the determinant, but you need to involve, well, I guess those type of Morita invariance constructions on the ghosts. So let me not do it. Yeah, thanks.
So the second bullet point does not involve the determinant map anymore.
No. Yeah. Yeah. Let me leave it at that. Yes, you're right. But you can describe the logarithmic derivative of that. But maybe I'm not going to do it now. Yeah.
And somehow also uniquely characterized the determinant map. So it grabs it on linear vectors, everything is a product. And
Right.
feel very
That's true.
I mean, it doesn't add any. Or, I mean, are you defining the characteristic polynomial?
No, I mean,
If I believe what chi of f is, then I'm not.
no. Think of it as sort of a description of what it does, which holds also for non-commutative rings. So that characterizes the characteristic polynomial when R is non-commutative by that thing. Let's say like that. Okay. Are there other questions? So what we did so far is I told you I want to try to lift the characteristic polynomial to self-adjoint endomorphisms, and we saw how to interpret the classical one in terms of Witt vectors. So now the challenge to fill up my square in the top right corner is to find some variation of the Witt vectors that sort of can host my lift of the characteristic polynomial. And for this, I'm going to find inspiration in topological Hochschild homology. Right, so, and now let's see if I can stick to my convention. So let A be a ring spectrum, and let's take it to be connective. because I'm going to have to assume it connective at some point. Okay. And now let me remind you, I mean, it's Bjørn's birthday conference, so maybe I should just go with THH and assume that everybody knows about it, but maybe let me not do that. So start with a connective ring spectrum, then Bjørkstedt, Chang and Madsen. So they define a genuine CN spectrum for every n. So Cn is the cyclic group of order n, called topological Hochschild homology of A. And I mean, there are many ways of doing this, and I'm not going to attempt a full definition, but here's some of it. So S spectra, at least, this thing is the tensor of two copies of your ring over the enveloping algebra. Everything tensor means derived mesh product of spectra of modules as well. Okay, so this is true as spectrum, and maybe if A is commutative or E infinity, then the category of infinity ring is tensor over spaces, so you can say that THH of A is A tensor of the circle. And at least this might convince you that there is some sort of cyclic or action of cyclic groups going on in this variable. And now you need to make it into a genuine thing, and I'm not going to say much about it. But you can define it as a genuine cyclic spectrum Cn for every n. And what does that have to do with Witt vectors is that Hesselholt and Madsen prove that if you take the equivalent homotopy groups of this spectrum, this is isomorphic to the Witt vectors of pi 0 of A. And now where is the n? Well, that's why I introduced those truncations, truncated n. Okay. And moreover, they describe transfer restrictions and these other cyclotomic structure maps on this side using Witt vectors operator. It's a beautiful theorem. Okay, and now I'm going to try to leverage this fact. So what's the point? The point is we saw the characteristic polynomial lives in here, or at least in the limit over n. But it's hard for me to guess algebraically something that could lift this characteristic polynomial for self-adjoint endomorphisms just from the Witt vectors. So instead, we look in topology, and maybe we can find a more straightforward way of generalizing this side instead, and then I can use that as my host for the characteristic polynomial. Okay, that's the strategy. So, so let's try to refine this one a little bit. And there is something I had on my original ring R that I haven't used so far, is the involution. Okay. So now let's run with this thought, and suppose. Now there is a bit of an awkward thing. You need to somehow put structure on A, and there are, depending on your point of view on the subject, you might do it in different ways. Let me try one way, and then we can have an argument about it if you want. So suppose that A comes equipped, and this is structure. So you have the structure on A. With the structure of a genuine Z-mod 2 spectrum. So there's one thing. So this is a Z-mod 2 spectrum, but it's also a ring spectrum, and you want some sort of compatibility between those two. And the compatibility is that this is a module, which is a module over the norm. So then I'm going to just write n of a, by which I mean you take your A that now I regard as a ring spectrum, and you can norm it up to Z mod 2. That's a new ring spectrum, and you want it to be a module over that. And the norm of Stoltz and Heat-Hopkins-Ravenel. Okay. Good. And then, well, let me just say it in such a way that if you restrict this by modules, this module structure on underlying spectra, you get the multiplication, the two-sided multiplication map of your ring. I'm not going to add that too. But here's the example to keep in mind. So example is when R is, say, commutative. Well, I mean not say commutative, maybe. Is a ring with involution. And then it's Allenberg-MacLane spectrum, by which I mean, it's Allenberg-MacLane ring spectrum. The Z mod 2 spectrum, I'm claiming it's comes equipped with the structure. And the Z mod 2 spectrum is going to be the Allenberg-MacLane spectrum of the Mackie functor induced by the involution. Is such a thing. And if you want to keep a formula in mind, which is very, very helpful, then you need to interpret it suitably depending exactly what you mean. But you can think that this module structure is given by, if you want to act by A tensor B, you do X A bar B. Okay. That's the formula to keep in mind. So now, if you are given such a thing, you can refine topological Hochschild homology. So in this case, THH of A, which was a cyclic spectrum for every n, Cn spectrum, it refines to a genuine dihedral group spectrum, by which I mean Z mod 2 semi-direct product with cyclic group. This new spectrum is denoted THR of A, where R stands for real. And again, I'm not going to define this in detail. I think hopefully Tina is going to tell us how to do that this afternoon. Thank you. But let me just say two things. That as Z mod 2 spectra, so hopefully at least this gives you an idea on why you need a structure. Well, what did we do before? We took A tensor ring over the enveloping algebra. Now A is a Z mod 2 spectrum, and it is not only a module over the enveloping algebra. As a Z mod 2 spectrum is a module over the norm, and now I can do that. Okay. And now you can ask, well, is this a left module or right module? And because you have this involution, you can turn those around. And this makes sense. So And if, let's see the other thing with the circle. It's gone now. If A is commutative, and now you need to be very careful what you mean commutative, but then we get that this is a tensor. So now this category of, if you say commutative right, this category is now tensored over Z mod 2 spaces, and you can tensor with the signed circle. So it's a circle with the reflection as a Z mod 2 action. Okay. And then again you see the dihedral group acting on this maybe, and that's how the dihedral action will be somehow constructed. Okay.
What do you mean by commutative?
I mean genuine infinity. Yeah. Yes.
But do you need also some sort of compatibility similar to some spectral Tambara functor?
Right. I mean, so for this description, yes. So I mean, I guess genuine infinity means a module over, an algebra over a suitable operand, and I guess then you can model those by spectral Tambara functor, presumably, because I'm not exactly sure that has been worked out, but I think so.
Yeah, and I also want to understand this notation. I mean, sphere. I mean, this is understood as what?
Sorry, I mean.
Tensor, the writing. I mean, the space. Yes.
Yeah. So.
Is genuine equivalent space or?
Yeah. It's a genuine. That's right. So.
No, which group?
Z mod 2.
Z mod 2.
Yeah. Right. Yes. This in.
This is not an action of this
I mean.
category.
Well. No. I mean. Okay. So there's no more complication than there is for THH. So for THH of A, when you write A tensor as 1, I guess you need. I mean.
It's just tensored over spaces.
Yeah. It's a tensor of a space, and then you can see how at least the circle acts, or in this case O2 acts, but then to give it the genuine structure you need to do some work, presumably. Yeah. I mean, yeah. So the way you do it, you just write down the bar resolution that does this thing, and then you subdivide enough times, and you see how to to put in the norms in such a way that it becomes a genuine O2 spectrum, or dihedral spectrum. Are there other questions? Okay. So why are we doing this? Well, so the key idea is use. So now we have, there was the theorem of Hesselholt and Madsen saying that it's up there, that the cyclic fixed points are the Witt vectors, and now we're going to use the fixed points for the dihedral groups. Or maybe of a, let's start with a discrete commutative ring, then of its cylinder-MacLane spectrum as our variant of the Witt vectors. And let's see why, I mean, that's a good idea. So, sorry? Oh, yeah, thank you. Yes. Yeah, I apologize for the R's. It's fun when you start doing TRR, then, and you have the R map, and so on. Okay. So far I have a definition, but maybe it's not so clear why that's a good definition. So let me try to attempt at this sort of a more explicit description of that along these lines here. So why do we call this Witt vector? I mean, why is that a good candidate or a good replacement as the Witt vectors? So here's a theorem that, and this I do need commutative. Then, and discrete. First of all, what happens when n is equal to 1? So the smallest dihedral group. So this is Z mod 2. And this is, you have this involution on R, so you can take its fixed points, and you can take two of them, and then mod out a relation by the subgroup generated by the expressions of the form AX, that's a Y, let's put the bars in the right order. Okay, so you can mod out this relation. Okay. So this gives you a description of what the fixed points are. And then, so if P is odd, not prime, and I really need it to be odd, then, so if you look at what happens for the, so for the dihedral group at a prime P, then what this is, it is the Witt vectors of that thing. So, the bottom thing is something. It is a ring because R is commutative, that's important. And so if you ask the question about higher powers of P, you get the Witt vectors on that. Okay. So at odd primes, you do get the Witt vectors on something. So not for P equal 2. And I'm going to treat the case P equal 2 separately in a few minutes. Before doing that, sorry? No, for every, no, R any commutative ring. There is no, sorry, yes, sorry, thank you. Yeah.
I mean, in this theorem, there is let R be a commutative ring.
Yeah.
And then if P is odd.
Yeah. So if P is odd and I take the dihedral groups for a prime P, then this is true. If I take a power of 2, it's not going to be true anymore. Yeah. And R, yeah, it doesn't matter. So if you take the prime 2, and R is a perfect field of characteristic 2, then this still holds, but in general not. Like for the integers, it does not.
And what about if you take a product of prime powers?
Yeah, I mean, I'm not sure if you have these exact sequences, and then you can sort of play them around. But because I guess if you take odd primes, nothing weird happens. If you take a product of two odd primes, but if you have an even prime in there, it becomes, I'm not completely sure exactly. But so let's work one prime at a time for now. So maybe I should put an example. I'm going to go back to this example in a second. If you take R equals Z, that's where this story kind of goes wrong. So what happens here? Well, Z will be a trivial involution when this thing you're tensoring Z over Z. And so you get just Z. So, and then in these odd cases, you get the Witt vectors on Z. So what this tells you is that this map, the restriction map to the cyclic fixed points, sorry, P to the n, it's an isomorphism for P odd. Okay. So basically, our new fantastic construction that we want to use to lift the characteristic polynomial doesn't do anything else than the old one. So our lift is not very good. So this is an indication that maybe at odd primes, nothing too interesting happens. I mean, if you don't take Z, then this thing might be a little bit interesting, but this Witt vector stuff doesn't really do anything too exciting. Okay, so here's the theorem. I mean, is that there is a commutative diagram. I mean, I can basically fill out the diagram from the beginning. So this is phi self-adjoint endomorphisms. we have the characteristic polynomial, values in the Witt vectors of R. And then here you can put these dihedral things, the restriction map to the cyclic fixed points, which is that by Hesselholt and Madsen. Then you can fill this up with something that you can call chi phi. Okay. So there are different ways of obtaining this diagram. I'm sure that Thomas, Jonathan, and Jay Shah are going to give us a topological way of doing this by constructing some trace map. The way I prove this is just by basically doing the same type of argument that we did for the usual Witt vectors by constructing it through coefficients, just in pi 0. Using the structure you have on this thing that is analogous to the Witt vectors.
What happened to there was supposed to be evolution and variance or something?
Did I forget something?
In your original...
Yeah, I mean, right. So this map factors through the fixed points of, yes. Right. This is a Mackey functor, so the map is equivariant for the trivial action there, so it factors through. Well, let me write like that. Yes, that's right. Okay, so I mean, maybe this is not too surprising. Right, so let's try to calculate something now. So we have this diagram. How about trying to figure out what that is? So the first example is what happens for, maybe let me decorate a truncation here also. Okay. And so for n equal to 1, so I'm going to use this calculation, the fact at least that here I know what the ZMO2 fixed points are, so I can try to describe this explicitly. So for n equal 1, and let's take P free for simplicity, so I can take everything as a basis, so our endomorphisms and form have matrices, and I can describe things in terms of that matrix. So chi1 phi of f is, well, it's going to be an element in here, and I'm going to describe it for you. This is the sum of, it's a long formula, so. So by components, I mean the entries of the matrices in the standard basis. So this is the formula one gets out, something. And maybe I want to call this whole thing, I want to call it the phi trace of f. The first coefficient of the characteristic polynomial is the trace. Okay, so it looks a bit like a random formula, but now let me try to argue that it's not. Or at least someone else has thought about it before. So here's a theorem. This shows up, I mean, once I was reading around and I found this paper of Cato and that formula popped out, so that's kind of nice. So if K is a field of characteristic 2, then you can look at the symmetric Witt group. I apologize for another W, but I can't do anything about it. So this is a symmetric Witt group. Okay, so it's isomorphism classes of symmetric forms where K, where you quotient out the ones that admit a Lagrangian. And now you can look at the trace, so of the identity as a function in phi. So the identity is always phi self-adjoint. So you can always look at the identity and vary the form. And this gives you a map to, well, to those M02 fixed points of THR. And in this case, because the field is of characteristic 2, you get, well, if you look at that relation long enough, you see there is just tensoring K as a module over the subfield of squares. So let's say subfield of squares. And what does it prove? It proves that this map is injective. Okay. So even the trace is sort of a good invariant on the Witt group. There's something slightly confusing here, maybe, that, oh, maybe that's not. Let's ignore this. Other questions so far?
About the notation in your formula.
Yeah.
So you have a sum over an I.
Yeah. So I goes from 1 to the rank.
What are those other little U's?
U's? No, there's no U. Hang on.
What are those?
Which ones?
I,
These.
Is that an I?
These are all I's.
Those are all I.
All these indices are I's. Yeah. So
What does that mean?
II is the II entry of the matrix. So it's the
I.
you look at the diagonal entries. Yeah. Sorry. Yes. So it looks like a bit like a trace, but you tensor these things together. Yeah. All right. So okay, let's leave this one. So the hope is that somehow by looking at, sorry, I just erased the formula. So the hope is that, the same way that this trace is invariant of on the Witt group, maybe these characteristic polynomials for higher truncations could be injective in cases where the trace is not. So let's see an example, which is not quite that, but in that direction. But the problem is that I need to look at the prime 2. So in the last couple of minutes, is it 2 or 3? 3. Let's look at what happens at the prime 2. Okay, so for odd primes, you can say that. And for the prime 2, I kind of gave up trying to compute it because I couldn't get anywhere. And I don't know, maybe Tina is going to tell us something about it or some way of thinking about it. So for now, at least until this afternoon, let's just ignore that and just work with, the realization that this is as good as we can do. But the point is that Witt vectors are a very, indirect construction anyways. And everything is seen through the ghost map. Everything is by induction on these exact sequences. So maybe if we can construct that structure at least, we can, we are good to go anyways. So let me say something about that. So now let's look at the prime 2. Let me say that this has structure similar to the Witt vectors OR, but with some pretty crucial differences. So let's do one. The standard thing is that there is a fiber sequence. So there is a restriction map that comes from the cyclotomic structure of THH. Okay. And now there's a fiber term. Okay, let me keep a bit of suspense and let me tell you what you should compare it with. So what happens if you do this in Witt vectors? Well, you have this restriction map, another map R. So this is surjective, same here, and the kernel is R. This is the Verschiebung, and this is injective. Okay, and these are the sequences you use all the time to do inductive arguments on N. And something similar happens here, but now the fiber is not R anymore. Well, you wouldn't expect it to be R. What is this R really? This is the sort of W1. Okay, so what is W1 here is pi naught z mod 2 of thr of R. However, it's not that. There are two copies of those. And I mean, why are these two copies? Is because inside this dihedral group, there are two reflections which are not conjugate, and this is the two reflections account for these two summands. And it's not only a sum. I mean, this map descends to the push out along the transfer map. This is, I think of this as being pi 0 for the trivial group of THH, and there are transfer maps that can push out like that. And this is not injective in general. Not injective in general. Maybe that's not too surprising. Verschiebung is not always injective for non-commutative rings. Here R is commutative, I should say that. So this is something.
But is it injective for somehow free enough guys?
Ah, that's very good. Yeah, that's right. So yes. So two answers to the question. So yes, but you need to make sure that you say free, right? So free as, you know, in terms of Z mod 2 spectra, so free as Tambara functors, say, or maybe as Mackey functors at least, which is annoying because polynomial rings are not. But then the surprise is that this does become injective for polynomial rings as well. But that's hard, and it's not, I don't know why that happens. But yeah, so that's right. So I guess the actual answer is yes, but for somehow non-formal reasons. Okay, there are only 2 minutes left. So let me say there are analogous ghost maps. Let me not spell out what they are. They're also going to have some weird sums because of that kernel. And these are not injective for commutative rings, not even for Z. So that makes everything much more complicated. But somehow, okay, so we have our characteristic polynomial in there. So how do we compute it if we don't know how to describe that thing? So here's one way you can try to compute it. So here's the theorem. Let's do it for Z at least. So there is a version for polynomial rings, but it's a bit more complicated to state, so let me not do it. So let's take THR of Z. Let's take these dihedral fixed points. Instead of taking the dihedral fixed point, let me do something else. Let's take the cyclic fixed points and then the geometric fixed points. Okay. And let's look at pi naught of that. So this is much easier to study than those fixed points. And in fact, this is isomorphic to a bunch of pullbacks of Z mod 4s over Z mod 2. And I think there are 2n copies, and this holds for n at least 1. The first thing. So at least the geometric fixed points we can describe explicitly, not really the genuine ones. But here's the funny thing. The map so how can we try to describe those if we know the geometric fixed points? Well, it turns out that if you start from the dihedral group, you can map to this thing when you do cyclic first and geometric, there's a canonical map like this. And you can pair that up with the restriction map to pi 0 to the Witt vectors, right? Pi 0 of the cyclic thing, which is the Witt vectors. And the funny thing is that this combination of these two maps is injective. at least for R a polynomial ring. Okay. So maybe we cannot compute things in here, but maybe we can compute them in there. And this composite is just the usual characteristic polynomial, right? Because it's just a restriction map. So really, this extra structure this extra lift is the extra information is picked up by the geometric fixed points already, at least in the commutative rings, for polynomial rings. And 1 minute over time, I apologize. Let me state the last thing. No. And so I get an extra minute for the board. So at least let me tell you what happens for Z as some sort of test case. So for example, so for R equals Z, you can take the characteristic polynomial of the identity. Let's take the n-truncated one for some form phi. This belongs to this dihedral, that's at the power 2. This belongs to these dihedral fixed points. And now if we map it to geometric fixed points across the Witt vectors, what do we get? Well, this component we said is a restriction map, so it's the rank. So this goes to the rank. But I just told you what this is for Z, right? It's that iterated fiber product of Z mod 4s, and here we see the signature in that, in that ring. But let me maybe spell out, because that's for torsion. This is the signature mod 4. Okay, so. A form is characterized, at least in the Grothendieck group, by rank X signature. This is not quite injective because we can only see it mod 4, but we see more than just the rank. So at least we see something for Z. And what I'm trying to do now is to come up with formulas to see what happens over polynomial rings in general, and find some formulas for these characteristic polynomials. Okay, I'm going to stop here. Thank you. Yes, exactly, diagonally. That's a bit boring. But it is because it's the identity. Taking ghost maps, right, is the trace of the powers of F. So for the identity, you just get the trace of the identity in every component. So that's exactly why. That's diagonal. Presumably, if you stick in something else, you're going to see something that is not. Yeah.
Do you have any ideas on what the other homotopy proofs in this thing?
So yes-ish. So for Z we computed everything on this side. Not really on that side. Thomas, Jonathan, and Jay Shah have a theorem that on this side you should get the normal L theory, so the cofiber of the map from the quadratic L theory to a suitable version of symmetric L theory. So in examples, this tends to be for periodic, and yeah. So I guess if you know L theory, then yes. If you don't, well, there are some other formulas you can use to try to calculate it. So it's a bit of a game of chess somehow.
There is something with Witt?
Yeah. So I've been thinking a little bit about that, and my impression is that possibly you can try to work out some sort of de Rham-Witt bigraded of arrow Z mod 2 graded de Rham-Witt complex. That's possible, presumably. I was not trying to do that. I was trying to see some de Rham-Witt structure on these, so on the geometric fixed points, and that doesn't seem to be. The problem is that you got a differential in the de Rham-Witt complex. When you take geometric fixed points, that differential becomes of degree 0. And so if you look at an initial object, you can guess what that de Rham complex could be, but it doesn't have a differential anymore, so the initial object is going to be 0. And so it's unclear what the right thing should be. So somehow one needs to build in some sort of periodicity, and yeah, it's not clear.
Sorry, one question about this relation. I mean, shouldn't we
Yeah.
get a D mod 8 and signature mod 8? Normal 8, you're saying that just...
No, no, this is TR, it's not TC. No, the Z mod 8,
This builds up in the extension.
yes, in the last extension. Yeah, yeah.
You see D mod 8, you see signature mod 8.
Yeah, it's funny. Yeah, so maybe one should go all the way up to TC to see at least 1 power of 2 more.
So do you have any linear version of this, I mean, instead of oversection?
Not really. Is Tina going to tell us what? No, yeah, not really. No.
More questions? No, then we're going to have a coffee break now, and we're going to resume at 11.
Thanks.